Our research is to find a method to identify optimal bin number for histogram binding method to calibrate binary probabilities. Receive operating characteristic or root curve analysis in machine learning are used to select the best for the given data set classification algorithm by comparing area under root curve. Root curve analysis is applied in areas medicine, finance, information retrieval, quality control, and others. For example, in medicine field, it is used to evaluate the performance of a diagnostic test, and it helps in decision making regarding test accuracy. In finance and e-commerce, it is used to assess the effectiveness of fraud detection system. In information retrieval system, it helps to optimize the trade-off between relevant and not relevant results. However, an accuracy of area under a curve imposing on a predicted probabilities threshold that it must be more than 0.5 for positive class. That is mean that when target class value is positive, then the predicted probabilities value must be greater than such threshold is applied only for probabilities predicted by logistic regression. Other often used classifiers such as random forest classifier, a support vector machine classifier, naive-Bayes classifier computes probability in different way. Random forest classifier predicts probabilities, in other words, scores, as a fraction of samples in a given class within the set of decision tree and force. Naive-Bayes classifier calculates the probabilities of data point from the data sets belong to a particular class based on Gaussian distribution of the feature. And support vector machine classifier does not provide probabilities. Instead, for each data point in the data set, it calculates the distance between the data point to hyperlink. Therefore, calibration of predicted scores is a required step, is a necessary step in order to execute a root curve analysis with the goal to select the best classification algorithm. As a benchmark method to calibrate binary predicted probability is used a histogram binding method. It was proposed and proved efficiently for algorithms such as random forest classifier and naive-Bayes classifier. The method for the interval from 0 to 1, it divides in 10 bins, and then it calculated that using this, it calculates the scale probabilities. The computation simplicity and ability to measure calibration error made this histogram binding method is often used. However, the method is effective with bin numbers when bin numbers is properly selected. As depending on a dataset characteristic, predicted scores are differently distributed through the bins, and too small or too big number of bins would cause over detailed or over smooth scaled probabilities. Though the picture on this slide illustrates how the areas under a curve can be impacted, made 2 times less when the scale probability are over smoothed. To improve fixed weight binding method, involve verified uncertainty calibration was proposed a scaling binding method. According to this method, the dataset is divided into 2 subsets. The first subset is calibrated by other continuous calibration method called plot calibration, and the second subset is used to choose the bin so that an equal number of points are landed in each bin. The scaling binding method addresses 2 issues: reduce calibration error and calculates bin width, which is adopted to already calibrate. However, A plot calibration method itself has a few problems. It is the most efficient when the distortion of predicted score is sigmoid shape, and it is computationally intensive as it's often a convex optimization problem to find sigmoid function parameters. In other research with title and new bin size index method for statistical analysis of multimodal dataset from material characterization to identify bin size to conduct a histogram for the dataset distribution is proposed to use a Friedman diagnosis. However, in statistical theory, depending on actual data distribution, it is recommended for the identification of the bin size and bin number of the estimators. That's what Friedman diagnosis, Stark's rule, Diana formula, Rice rule, and others. So, utilizing only Friedman diagnosis rule may not result that optimum bin number is found. The current research objectives are to empirically study whether the simple statistic of uncalibrated predicted binary scope can be used to choose optimal bin numbers for the fixed width binary method and to propose a solution approach. To achieve the research goal, we consider the simple statistic of the predicted scores, range, standard deviation, and interquartile range, and bin size estimators, David-Scott rules, and Friedman diagnosis rules, as the result are directly proportional to a standard deviation and interquartile range corresponding. Our methodology includes two feasibility studies for different approach to find optimal bin numbers. The first approach is a rule-based approach. The second approach is estimator-based approach. The rule-based approach suggests having a set of rules which, depending on the simple statistic of predicted uncalibrated scores, will propose an optimal bin number to be used with a fixed width binary. The estimator-based approach suggests identifying bin number by using different estimators and selecting the best bin number to be used with fixed width binary method as a result of evaluation of a calibration error. Feasibility study for rule-based approach includes set rules with input parameters, simple statistic from predicted uncalibrated scores. Specify the expected result. Execute the rules and report the actual result. Compare actual and expected result. If actual and expected result are the same, then recommend the rule-based approach. Feasibility study for estimator-based approach includes steps. Calculate bin numbers using selected estimators. Calibrate predicted scores with a fixed width binary method and bin numbers received from step 1. Then compare actual result and expected result. If the minimum calibration error does not correspond to bin with a number 10, then propose estimator-based approach. To execute the rule-based approach, we set rules. The first rules consist of two clauses. First clause, given predicted scores have a low standard deviation and the score variability is small. And the second clause is, given predicted scores have a low standard deviation and scores variability shows a degree of dispersion. Then our expected result will be, when David-Scott rule calculate the required bin numbers for the first clause and the second clause corresponding to that, the result should be close as David-Scott rule is not expected to care about scores range. Second rule, given predicted scores have a low standard deviation and a low interquartile range and the score variability show a degree of dispersion, then the expected result will be when David-Scott rule calculates the required bin number and Friedman diagnosis rule calculates the required bin numbers, and the result are close as both estimators are not expected to care about a score range. In case the actual result from the execution of rules to the same as expected, then our recommendation would be to develop rule-based approach. To execute the estimator-based approach, we selected two metrics to evaluate calibration error. The first matrix is a Brier score. The calibration error calculates as a mean square of the actual target class and predicted binary scores as specified in equation number 1. Second metric is expected calibration error that calculates error as a weighted average between the difference between the mean of the actual target class values that belong to a single bean and the mean of calibrated scores which also belong to the same single bean. We selected those two metrics in order to be sure that our evaluation of the results is correct. Also, for visualization of the result, we use a calibration curve plot. That calibration result depicted as a relation between the mean predicted binary scores in each bean placed on x-axis and fraction of actual values of target class in each bean on y-axis. To calculate bean number and bean width for each dataset, we use two estimators. David Scott estimator, it makes a bean width to be proportional to standard deviation and inversely proportional to the number of observations in the dataset. And Friedman-Giaconis estimator, it makes a bean width to be proportional to interquartile range and inverse proportional to the number of observations in dataset. For the calculated bean width, the number of beans is calculated as a fraction between the scores range and the bean width. Algorithm of fixed width binning method specifies the following. In line as input parameter, it takes the number of beans, right, and the uncalibrated predicted scores. In line from 6 to 8, it calculates bean ages using interval from 0 to. In line from 9 till 14, for each uncalibrated score received as input parameter, it calculated its index of bean. In line from 6 to 18, the algorithm iterates through beans indices, finds scores which indices coincide with current bean index, that score index are denoted as mass, and calculate calibrated scores as average of the score inside the bean. Our proposal for the estimator-based approach is to calculate bean numbers with estimators before calling a fixed bean binning method specified per algorithm. So you can see that in line 6, bean width is calculated by estimators. Then in line 8, predictor scores are calibrated by algorithm 1, which is called with bean number calculated in line 6. In lines from 9 till 10, the calibration results are evaluated by Brier score and expected calibration error, and the marks are recorded. Then lines from 6 till 10 are repeated for each estimator, and in lines from 12 till 16, the optimal bean number is selected when the lower value of matrix is identified. If matrix marks this green, then the default bean number equal to 10 is going to be used. In case the minimum calibration error, which is received from the execution of algorithm 2, is for calibration with a bin number different from 10, then our recommendation will be to develop estimator-based approach. Our experiments execution for the rule-based approach consists of steps. First, calculate bin widths using estimators and bin numbers according to the specified formula with input parameters. And then for each rule, we specify input parameter. Rule number 1. We put standard deviation less than 0.1. We put the number of observations with 250 and score range is low less than 0.1. Rule number 2. Input parameter differs only by score range, that is in the interval from the 0.5 till 0.7. And then rule number 3 differs from rule number 2 because we use interval type range, that is low, it's less than 0.1. Then we execute these rules, compare results with expected results, and make recommendation. The execution of the feasibility study for estimator-based approach consists of generate two synthetic datasets for classification problems. The first dataset is from skewed Gaussian distribution. The second dataset is from the normal distribution. The size of dataset is thousands of observation, and target class has value 1 for positive class and 0 for negative. The machine learning algorithm that in scope is a random forest classifier and name-based classifier, and those algorithms are executed with the default values for hyperparameters. Split data set on train and test subset in proportion 80 to 20. Train learning and then receive predicted binary score on a test subset. Execute algorithm 2. Compare actual results and expected results, and we will make a recommendation. Our result for the rule-based approach is the following. From the execution of rule 1 and rule 2, we receive that a small change in the score variability impacts David's squad rules result, so the calculated number of pins differs approximately by a factor of 6. So it is 29 in the first rule and 5 for the second rule. That is not expected, as David's squad rules are not expected to consider the changes in score range. The actual results which are obtained from the execution of rule 2 and 3 show that both estimators calculate number of bins which differ by a factor of 12, which is again not expected as we fix to be low standard deviation and interquartile range. To summarize the result, we won't recommend rule-based approach, as stable rules cannot be defined based on selected simple statistics. The results for estimator-based approach for the data set from the skewed Gaussian distribution. When predicted uncalibrated scores have a low standard deviation and low interquartile range, and as specified in line number 1, then the optimal bin number can be equal to 60 as reported in line number in table 2 and calculated by Greenman-Japanese rules, and this bin numbers is optimal according to two metrics, Bridge-score and expected calibration. When predicted uncalibrated score spread is low, however, standard deviation and interquartile range are increasing, as specified in line 2 from table 1, then the optimal bin number is calculated as 8. I'm referring to table number 3, and the result is from a David slot rules. Calibration curves. For naive Bayes classifier calibration curves depict that on picture B and picture C from line 1 we see almost similar number of beams which are close to diagonal. At the same time, on picture A, for 10 beams, all calibrated scores are distributed in 4 beams, from which one is only diagonal. For random forest classified calibration score, calibrated curve on picture C from line 2 shows more curve points are close to diagonal line compared to curves on picture B, which indicate the beta calculation with 8 beams. The results for the estimated Bayes curves with a data set from a normal distribution. Table 4 records a simple statistic for predicted by naive Bayes classifier and random forest classifier uncalibrated binary scores in line 1 and 2. The calibration result scores from table 4 are presented in table 5 and 6. At table 4 records increased spread from mean and median in the predicted uncalibrated score. So in table 5, it seems that number of beams is close to 10. It is 12 and 8. In table 6, due to more increased spread, we see 6 beams are needed and is recorded as optimal. Calibration curve. For naive Bayes classifier calibration curve, on picture C, line 1 shows 5 from 8 curve points on diagonal, which is an indicator of good calibration. For random forest classifier calibrated scores, the low value of metrics are captured from 6 beams, and calibration curve on picture B and C in line 2 indicates better calibration compared to the calibration curve for 10 beams, which is on picture A. The summary from our study is, in the current study had been considered 2 different approaches for identification of the optimal beam numbers to be used for the fixed width binary method. The rule-based approach, according to which a set of rules depending on the value of uncalibrated score range, standard deviation, and interpretable range would cause an optimal beam number, had not been recommended to be further developed, as the actual result from the rules execution compared to expected results showed that small changes in the score variability may impact the David Scott result, and the David Scott results and Friedman diagnosis rules calculate the number of wins, which differs by a factor of 12, which is not expected, as we fix to below standard deviation and interpretability. Our conclusion for rule-based approach is that stable rules cannot be defined based on the selected simple statistics. The effectiveness of estimator-based approach, according to which beam number is calculated by different estimators, and the optimal beam number is selected as a result of the evaluation of a calibration curve, revealed the following. 10 beams for the fixed width binary method to calibrate predicted probabilities is not optimal for all data. When uncalibrated scores range, standard deviation, and interpretable range are low, then 60 beams can be optimal according to Friedman diagnosis rule. At the same time, when score spread is low, our standard deviation and interpretable average are increasing, then 8 beams can be optimal according to David Scott rules. Using fixed spread, whose optimal beam number is decreased to 6 beams according to both estimates. Our proposal is to identify beam number dynamically according to estimator-based approach, which is described per algorithm 2. The proposed algorithm will improve calibration of the binary predicted probabilities based on expected calibration error and Bayes metrics, which is visible from calibration curves on figure 1 and 2. The future work we will consider to extend the proposed estimator-based approach by including more estimators such as Starker's formula, Rice rule, Diana formula, as those estimators consider B number based on the range of the data. Thank you very much for your attention.